Now let's review the interactions of photons with matter. Photons are electromagnetic radiation with no electric charge and no rest mass, and they always travel at the speed of light c in vacuum. Because photons are electrically neutral, they do not interact with electrons and nuclei through Coulombic electric force. Therefore, a photon's interaction with material is not gradual, but is characterized by the sudden disappearance of the photon, or by scattering through significant angles with significant energy loss. The type of photon interaction depends on the energy of the photon and the material it interacts with. In this particular unit, we have learned about 4 types of interactions of photons with matter. 1. A photon with the exact amount of energy hf that equals to the energy difference between 2 energy states can cause an electron in an atom or a molecule to transition from the lower energy state to a higher energy state. In this process, the photon disappears and gives all its energy to the electron. The photon energy has to be exactly the difference between the energies for the 2 states, E upper minus E lower, because at the higher energy state, the electron is still bound by the atom. According to one of Bohr's postulates, an electron in orbit has a definite amount of energy, so the electron cannot take in any extra energy. If the photon does not have the right amount of energy, it cannot be absorbed by the electron in such manner, and therefore cannot cause energy state transition. 2. The photoelectric effect. In the photoelectric absorption process, a photon undergoes an interaction with an atom in which the photon completely disappears. In its place, an energetic photoelectron is ejected from the atom. The photoelectric effect usually happens when the incident EM radiation is in the visible light or UV range. For photoelectric effect caused by X-rays or gamma rays, the most probable origin of the photoelectron is the tightly bound inner shell electrons of an atom. The photoelectron appears with a maximum kinetic energy that equals to hf, the photon energy, minus the phi, the work function. Because the ejected electron is no longer bound by the atom, it can absorb photons with extra energy, and the energy left over after overcoming the ionization energy becomes the kinetic energy of the ejected photoelectron. 3. The Compton effect or Compton scattering happens when an X-ray or a gamma-ray photon is scattered by an electron inside a material, and the electron gets knocked out of its atom in conjunction with a new scattered photon. Because some of the original photon's energy is given to the electron, the new scattered photon has less energy than the original photon. When a photon carries less energy, its speed still is the speed of light, but its frequency is lower and its wavelength is longer. 4. Pair production. When a gamma-ray photon with photon energy more than twice the mc squared of an electron enters matter and gets close to a heavy nucleus, it may disappear as a photon and reappear as an electron and a positron pair. This has to happen next to a heavy nucleus in order to keep momentum conserved. Again, the type of photon interaction depends on the energy of the photon and the material the photon interacts with. Although there is overlap in the types of photons involved in these various interactions, usually electron or atom state transition and the photoelectric effect involves visible light and UV photons. Compton effect involves higher energy X-ray or gamma-ray photons. As for pair production, it involves even higher energy gamma-ray photons.